Testing, testing. Testing, testing. Hello everybody, welcome to Slooh. I'm Paige Godfrey and I'm going to talk to you tonight about the solar system. You are tuning in to my Intro to Astronomy course. This is the second session and tonight is the solar system broadcast. So we're going to talk about what's in the solar system, how the solar system was formed, what's going on with the dynamics around our solar system. What does this have to do with the Gemini meteor shower coming up? A whole bunch of fun things tonight. And I am sharing my screen with you, so hopefully you can see all of the things that I'm doing. Right now, I'm on Slooh.com's telescope page. I thought we would just start the night off with looking at what our telescopes are looking at. We're fortunate. We've got the Canary Island scopes online tonight. And so you can see I have set up for us on Canary 4 and Canary 2 the Uranus missions. So if we visit the telescope page, we can see Uranus. Here we are. And I chose these tonight because they are the current planets that are visible through our telescopes right now. Jupiter is going to be coming into view soon, and I'll give you a little preview of that a little bit later. But I wanted to focus on the planets for tonight because I think that a lot of times when we talk about astronomy, we talk about so many extragalactic things and dark matter and supernovae and really phenomenal things that are happening, but I think that our own planets get overlooked a lot. And so I wanted to do a nice session tonight on the solar system. And so we're going to start off and talk about exactly how is our solar system structured. What do we've got in it and how is it formed? And so I'm sharing with you right now an image that I love from theplanets.org. It shows our sun on the left side of the screen, and then all of our planets, of which there are 8 major planets, and then our dwarf planets, Pluto and Eris and Makemake, and we see our asteroid belt between Mars and Jupiter, our Kuiper belt objects out beyond Pluto, and then even further out past that, we have what we call the Oort cloud. So what does all of this mean? When space first came into existence, we had the Big Bang, we had this huge explosion of space and time, and all of this matter, which was semi-homogeneous, semi-isotropic, all the same in each direction, but also kind of not. It was kind of clumped together in these weird like clumps with strings like pulling off into each direction, and this clumpy matter started to collapse under its own gravity. And it would form these clouds of gas and dust. And out of these clouds of gas and dust, we would get solar systems. So when we have a cloud of gas and dust in space, it's got a gravity, it's got a center of mass and a center of gravity, and the gravity of the center of mass starts to overcome any of the forces that are keeping the gas cloud stable, and it begins to collapse in on its center. And as it's collapsing, it starts to rotate around itself, and the further it collapses, the more it starts to rotate because of the conservation of angular momentum. And then in the center of the gas cloud, you get this really dense, hot fireball of gas, which is a star, and in our case, our sun. Now, around the star that's forming, there's still some gas and debris that hasn't coalesced into the star in the center, and that keeps rotating, and it starts to flatten out due to the angular momentum of the rotation. And this flattening out of the gas and dust we call a protoplanetary disk. It looks like a disk-like shape around the center star, and within it, again, with this whole clumpy matter idea, we start to have rocks and little tiny rocks. I'm talking about dust particles, but rocks and gas particles that are bumping into each other at such high speeds. And because they stick together. And the more that start to stick together, the higher the gravity of that particular clump. And so then it starts to pull in more because of its own gravity. And we call that accretion, when an object has enough mass that it starts to pull particles and debris into it. It's accreting mass. So we have the sun forming in the center of this collapsed gas cloud, and then around it is the protoplanetary disk where the planets are forming. And so you can kind of imagine when you're looking at this image here that you see our sun in the center, and all around it, out all the way to the Kuiper belt, we had our planets forming. And these all formed in our disk. And so because of the way that they formed, there's some categories that we can put these planets and their moons into, and some different physics that went on based on how close they were to the sun when they formed. In particular, one of the things we'll talk about tonight is moons, and how the number of moons is semi-dependent on the size of the planet, which is also semi-dependent on where it was in the protoplanetary disk when it formed. So I said we have 8 planets. We have Mercury, Venus, our Earth, Mars, Jupiter, Saturn, Uranus, and Neptune. And then I've said 8 because if you remember, Pluto has been demoted to dwarf planet. This was because back about a decade ago, the IAU had to define what an actual planet was, because we started finding things like Eris and Makemake out beyond Pluto, which are dwarf planet size. I mean, they're similar size to Pluto. We called them dwarf planets. And so what constitutes a planet? How come all of these aren't just planets and we have hundreds of them? So the International Astronomical Union came up with the definition of what constitutes a planet, and it's 3 main restrictions. The first one is that an object has to be in orbit around the sun. Makes sense. The second is that it has to have sufficient mass. I'm going to use some jargon here and then I'll explain it. Sufficient mass for its self-gravity to overcome rigid body forces so that it assumes a hydrostatic equilibrium. Basically, it has to be nearly round. It has to be massive enough that its center of mass, its gravity, is pulling in every single direction so uniformly that the object forms a sphere. And then the third restriction is that it has to have cleared the neighborhood around its orbit. So, as you can imagine, Earth is orbiting the sun, and we don't have anything in our way, fortunately. But if we had a bunch of asteroids in our way, we would not have cleared our orbit. And what should have happened is that we'd either kick these objects out of our way, or we would accrete them onto ourselves. And so this is what we define as clearing the neighborhood around our orbit, and this is what Pluto has not done. So Pluto does orbit our sun, and it is round, nearly round, but it has not cleared its neighborhood. And that's how the IAU has now defined a planet. So then, if we look at how many moons we have, actually our moon is on this image, which I find entertaining because none of the other moons are. How Pluto's is. But when we define how many moons we have, we note that Mercury and Venus, I'm going to pull up a list here from NASA's website. Mercury and Venus don't actually have any moons. Earth has a moon. Obviously, we just have our one moon, which is what we called the moon. And then Mars has 2, Phobos and Deimos. Jupiter, you can see this list on the right here. I'm going to scroll all the way down. Jupiter has 69 moons, some of them which are not named. You can see if they have a year in the name, that means that they've been inferred in existence, but they haven't been fully observed yet to be defined as a moon, and so they haven't been given names. But as soon as they are detected, for sure, they will be given a name just like the rest of the moons. Saturn has a bunch of moons, 60 of them. Uranus has nearly 30. Neptune has 14. And Pluto has 5, one of which, Charon, is nearly the size of Pluto. It's actually about half the size. So we have all of these moons. And what's interesting, what I find really interesting, is the numbers of the moon is based on the kind of planet that it's orbiting. So Mercury and Venus, which are small and really close to the sun, don't have any, and yet Jupiter and Saturn and Uranus, which are all out further away from the sun and are much bigger planets, have a ton of moons. And so if you're noticing a pattern here, so am I. What's going on is that when our solar system formed, and this isn't unique to our solar system, we see this happening in other solar systems as well, the closer the planet is into the sun, it's typically a rocky body. As you can see, Mercury, Venus, Earth, and Mars are all rocky planets, whereas Jupiter and Saturn are gas giants, and then Uranus and Neptune are icy giants. And so there's another pattern. The closer you are to your sun, the warmer your planet, of course, and so you're a rocky planet. And then the big gas giant planets are further out, and then even further out, now the gas has turned into ice. And so we have our ice giants, Uranus and Neptune. And the reason that the gas giants and the ice giants have many more moons is because these planets are so much more massive that when our protoplanetary disk was forming and these planets were forming, their extra mass allowed them to pull in extra debris to be moons. So moons can form in a few different ways. One of which is that while the planets are going around this protoplanetary disk, remember I said the gas cloud is rotating, and this is why the sun still rotates, this is why we orbit the sun. The moons can kind of form in the same way that the planet does, and then the planet just captures the moon, basically kind of kidnaps it and says, you're going to be my moon forever. And when a planet has much more mass, it can capture many more moons, which is why Jupiter and Saturn have so many and why Mercury and Venus don't have any at all. They weren't massive enough to hold on to some of this debris. And the other thing that we can consider is where the debris was located. So we have this asteroid belt and the Kuiper belt, which are out further away from the sun. We have much more leftover debris out there because it hasn't been as greatly affected by the sun's gravity as debris would be if it was near Mercury and Venus. So when we talk about how far away something is from the sun, let's define a unit here to help us kind of understand how far away I mean when I say, oh, it's out much further than Mercury. So one of the units we've defined, because when we go into cosmic distances, they're so big that talking in miles and kilometers isn't a very useful unit of measurement. And so we defined the astronomical unit, the AU, or we'll refer to it as, which is equivalent to 1 Earth to sun distance. And so the distance between the Earth and the sun is about 93 million miles, or 150 million kilometers. And we say about, this is an average because our orbit around the sun is elliptical, not circular. So the distance between the Earth and the sun changes. So we take an average of it. And these 93 million miles we call 1 astronomical unit. So in this figure from the Griffith Observatory, you can see that Earth is denoted as 1 AU from the sun. Mercury and Venus, of course, are closer. So Mercury is about a half of an AU and Venus about 3/4. And then Mars is 1.5 AU. Jupiter 5, all the way out to Pluto, which is nearly 40 AU away. And for another reference, in the discussion boards the other day, I posted about the Voyager 1 spacecraft, which has left our solar system and is out in interstellar space. We were able to fire the backup thrusters all the way from Earth on Voyager 1, which I just thought was insane considering how far away it is. But for your reference, how far away it is 140 AU, which is equivalent to about 13 billion miles. So this is no small distance here. And, you know, of course, we have bigger measurements denoted like light years and things for when we talk about objects that are, you know, across our galaxy and out beyond our solar system. And we'll define those in later episodes. But for now, we're going to keep track of the astronomical unit. So the moons of our solar system actually are in two different categories. We have regular moons, which have what we call prograde orbits. Prograde meaning that they orbit in the same direction of their planet's rotation. So if you can picture this with me, the gas cloud, when it was forming, collapsing to form our solar system, was rotating. Therefore, the sun rotates. Therefore, the planets orbit the sun. And the planets rotate around themselves. So they orbit the sun, and then they have a rotation axis, which they rotate around themselves. So when a moon orbits in the same direction that the planet is rotating, we call that a prograde orbit. When it's orbiting in the opposite direction of the planet's rotation, we call that a retrograde orbit. So a regular moon has a prograde orbit, and it actually lies nearly in the plane of the equator of the planet. When the moons were forming around the planet, the same way that our planets kind of formed around the sun in a plane, the moons also formed in a plane around the equator of the planet. Then if we have an irregular moon, that means it's either got pro or retrograde orbit. It doesn't necessarily have a prograde orbit, but it also lies at an extreme angle to the planet's equator. And so that means that that moon probably didn't form in the way that we would expect a moon to form, where it's the gas that's around the planet forming makes its own teeny little disk, kind of like the rings of Saturn. If you're looking at this image here with me, maybe this will be helpful. You can see the rings of Saturn, and so that's where we would expect a moon to form when the planet was forming. That's what I mean about the plane of the equator. And so if it's at an extreme angle, kind of where my mouse is, and it's not in the plane of the equator, and it would rotate, orbit around the planet something like this, like a weird angle, it's called an irregular moon, and it's likely that it was actually a really small dwarf planet, like an object out here, that was captured by the planet when the planet was forming. Instead of it forming around the planet itself, it was already a rocky body floating around that was then captured. And actually, our moon, we think, formed when a body about the size of Mars crashed into Earth in the early solar system and broke off pieces of that Mars-sized body and some pieces of Earth as well. And then it stayed in orbit around us because of Earth's mass. So we don't actually think that our moon formed from, sorry, I'm just getting a message that you can't actually see my mouse, so I apologize for that. So I guess the extreme angle I was trying to point out didn't really work, but if you look like diagonal or perpendicular even to the rings of Saturn, that's what I was referring to when I was saying an extreme angle orbit. So, but then, yeah, our moon probably didn't actually form in the way that other moons, like regular moons, do. It probably was formed when something crashed into us and broke off and stayed in orbit about us. So if we go back to Slooh's telescopes, we are on Canary 2 again, and I'm actually just going to go back to the main page and refresh. Yeah, we still have it in Canary 4. Let's zoom in there for a second just to see the pretty picture. So we'll wait for the color image to come in, but Uranus is a blue-green color, and that's because of the methane in its atmosphere. And so methane is one of the things that I'm a little bit partial to as a brown dwarf astronomer, because methane is what we use to define a T-dwarf, which is a really cold brown dwarf, which is almost similar to massive Jupiters. So like 50, 60 Jupiter mass objects. And so I think methane is a pretty cool element to be watching for. But if we go back to Canary 2, we might be able to see Uranus's moons. So let's just wait for this to load. Oh, it's coming into view. So we'll give that a good second. And I'm going to pop over to the Sky and Telescope where we can see the Uranus is in the center of that black box and its moons are around it. And so the moons closest to Uranus we might not be able to see because they'd be outshined by the light coming from Uranus, but we might be able to see some of them. And, oh, I keep clicking on the wrong screen. So we are back here on Uranus, on Canary 2. And so let's zoom in. And compare. This might be one of the moons. If you, oh, my image just reloaded. Okay, we'll do this again. I just got to the end of my mission. There we go. If you hear any background noise, I apologize. The fan on my laptop is running at very high speeds at the moment because I have so many things open. So actually, let me close a couple browsers while I'm here. Zooming back in again. All right. So yeah, so we're looking at a couple of Uranus's moons right now, I think. So if we look here, oh, this is just me flipping the view of like where the moons would be located. You can see some of the moons coming off of Uranus. And so these are some of the more major Uranian moons. Let's zoom back out. So you can't see my mouse, but you might be able to see on the left-hand side, I've got the plus and minus buttons, which is what's allowing me to zoom in and out on this telescope footage. And then another cool picture I wanted to show you tonight as well is of Jupiter. So Jupiter, you might have noticed if you've been trying to make some reservations lately of the solar system planets, hasn't been on there because it hasn't been in our night sky. But as astronomer Paul Cox just posted the other day, that we were able to catch it about 17 degrees above the horizon now because it's starting to come into our sky and it's going to keep climbing higher and higher. And the image that he shared, if you just double click on these images, these thumbnails, then you can view them in larger space, is on the left-hand side is an image from June when we had really good views of Jupiter. And then the image on the right is the first one of the season where it's only about 17 degrees above the horizon, so it seems a little bit smaller. That's just apparent, you know, it's not growing and shrinking actually, but it's also a little bit blurrier, and so as it starts to climb higher and higher, we'll get much better views of it, like on the left, but this is really great on the right. You can see the weather around Jupiter in the red stripes, and I'm going to actually go to my pictures because I have an image of Jupiter from the summer. Let's filter by solar system. And you can see the great red spot. And so I'm going to just take a moment and go show you that. It's probably all the way on the last page. Yeah, of course. Here we go. Here's my color image from June. And you can see the great red spot right there. It's on the, if you look just below the second like red ring, you can see the great red spot. Okay. So now let's go back to telescopes real quick because Chile just came online, and so I actually have Neptune on the Chile scopes right now. And so if you're doing this with me, if you're actually on the telescopes page, there's this camera button down at the bottom of the feed where you can snap pictures if you want. So we are looking at Neptune right now. Neptune also has a bluish tint because of methane in the atmosphere. So methane was something that we weren't expecting it to be so common, actually, in gas and ice giant planets. And it turned out to be common. And now it's actually one of the tracers that we're looking for when we look for life on other planets, because the particular, and now I'm not a chemist and I don't pretend to be, so I'm not going to try to name any ratios here, but the amount of methane compared to some other molecules in the atmosphere, depending on the ratios, the only way for that to be possible is if there is life that is using and producing the methane on the planet. And so if we can ever find that particular amount of methane in the atmosphere in the right kind of ratios, then that might be some signs of life down below. So we have Neptune coming back into view. It's really great all the telescopes are online for me tonight. This is perfect. So I'm going to keep closing browsers because my fan keeps running on my computer and my computer cannot handle this. But speaking of life on other planets, and so I'm going to just wrap up here with probably one of the biggest questions even all astronomers have, and many humans as well, is where is there other life? And we pretty much know that we do know that there are no aliens running around our solar system, but we're not 100% sure that there isn't life in the form of microbes or little teeny tiny cells on other planets. And the reason for that is because we can't get that close yet. So the only object in our solar system that humans have set foot on other than Earth is our moon. Really, we've explored so much of our solar system by probes, but we haven't actually gone anywhere else. And we've actually just so if you joined us back in September, we talked about the Cassini spacecraft that had been monitoring Saturn and its moons for a while, and it just crashed into Saturn's surface. We crashed it on purpose because it was done its mission, and it was going to die, and we needed to get rid of it so that it didn't interfere with any of Saturn's moons and potential life that could be on them. But one of the things that it found on Saturn's moon Enceladus is these plumes that are spewing ice, these jets of icy matter that are coming out of these plumes on the moon. And in them, we've found organic material, and we know that there's water. And so some of this is basically the ingredients that we should be looking for when we say that we want to look for life. So one of the proposed missions now, as a follow-up to Cassini, is to go back to Enceladus and to fly through the plume of ice to see what's in there, because just getting close to it and looking at it isn't really good enough. We need to get right in through there. But, then you also run into the potential of, if there is any sort of microbe in there, are you destroying it by blowing through it? And if you are destroying it, will you even be able to detect it? So that is something that we definitely have to consider when we talk about missions like this. But we do suspect that these icy jets that are coming off are because of an underground liquid ocean. And so when we're talking about maybe we could detect some organic life in the plumes, it's because they could be living in that underground liquid ocean. Because you might remember that I mentioned, these objects out there are really, really cold. And so where would there be liquid water? And it would have to be down closer to the core of the planet. The moon. Sorry, we're talking about Enceladus, but same thing applies, how cold they are, and it would have to be down closer to the core. You wouldn't have the liquid water on the surface. I just meant to say moon. But the source of energy that Enceladus would have to create the heat underneath the surface would come from the friction that's created when it orbits Saturn. So just because these objects are super far away doesn't mean that they don't interfere with their planet at all. We have winds, we have the gravity, and these forces, this air resistance, it causes a friction in the atmosphere, and it will create energy and heat that will heat the core of these moons. And the organic compounds that are the building blocks for life could be in this liquid water ocean underneath the icy surface. I'm going to go back on our telescopes to Uranus again, but keep talking about how moons affect planets, and like we talked about last week with our tides on Earth being created by our particular moon. So not only are planets a good place to look for life, but we're finding that moons actually are too. And of course, the infamous Mars missions that are being proposed, especially by Elon Musk. We know that there's no life on Mars, but we also think that it's possible that there could have been had Mars developed in the way that Earth did. And we actually think that the life on Earth may have come from Mars back in the very, very early solar system. But originally, back when we started first looking for life, and this was really well described in the book Pale Blue Dot by Carl Sagan. I just finished reading it, and I highly recommend it. It was so good. But he mentioned how we first started looking to Venus because we knew Mercury was going to be way too hot. But Venus seems really similar to Earth in size, and so we thought, it would only be a little bit warmer. And we thought because it has such a thick cloud deck around it, that it actually might keep the surface at a reasonable enough temperature to host life. But it turns out that Venus is actually even hotter than Mercury, even though Mercury is the closest planet to the sun. And that's because of what we call a runaway greenhouse effect. So you might be familiar with the term greenhouse effect because of the global warming on Earth, but a runaway greenhouse effect is when it just keeps getting worse and worse and worse. So when Venus has all these thick clouds in the atmosphere, the radiation from the sun comes down through them, hits the surface of Venus, and reflects back off, which happens on our Earth as well. This is why when you lay on the beach, you get sunburnt. So the radiation is reflecting back off of the surface of Venus, but because of the thick cloud deck in the atmosphere, it can't get back through. And so it winds up just reheating the surface of Venus and making this cloud deck and atmosphere even thicker. And so now more sun comes in and even more of it gets trapped, and this cycle just keeps going, and that's why we call it a runaway greenhouse effect. The atmosphere on Venus has become so dense due to this that the air pressure on the surface is 90 times greater than that on Earth. So if you tried to stand on Venus, you would be squashed. And it's so dense in carbon dioxide, so this heat that is coming through the atmosphere is actually heating up the rocky surface and releasing carbon dioxide from these rocks. The surface of Venus is also so hot that it could melt lead, and it could also boil mercury, which is not somewhere that we would want to live. So if we're going to move anywhere, it's probably going to be off to Mars, where we're going to have to build ourselves some biodomes, because terraforming Mars would be a very difficult task. But as I mentioned, it's also possible that we should be checking on moons for places to live. I mean, why not set up a biodome on the moon, which is a lot closer than on Mars? And I'll just, mention, Carl Sagan also said in the book, we talk about searching for life and the search for where we could move to as humans off of the Earth should we need to. And I feel like there's two schools of thought on this. And the first one is, we are so fine-tuned to our planet. It is so perfect for us to live here. Why should we look elsewhere when we should be trying to fix what we already have because it's so suitable to us? And there are a few reasons for that, and it's mentioned in Pale Blue Dot that two of the vulnerabilities we do have on Earth are global warming, as I mentioned earlier, but the issue is that we might not be able to reverse the damage. So even though if we work really hard, we can slow it down and buy ourselves some extra time, it might not be irreversible, and eventually our planet may look like Venus with a super hot and really dense surface because of the thick atmosphere. But the other thing that we're vulnerable to on Earth is asteroid impacts. And, what wiped out the dinosaurs, we think, is something that could happen to us again. And this is why we have near-Earth asteroid tracking systems and members of Slooh that are doing it. And I'm going to talk about that a lot next week. But, if an asteroid came and wiped out the human race on Earth, we are nowhere else to be able to begin again. So moving off of Earth might not be such a bad thing, but it's said really well in a short story that you can find in our anthology called The Saturn Above It. I'll actually go back to the homepage so I can show you what I'm talking about when I'm saying this anthology. Oh, you just got a glimpse of my gravity points and rank. but this is the book I'm talking about, The Saturn Above It. It's an anthology of a bunch of short stories, and one of them is by author Ray Bradbury, and it's about a father of an astronaut. And at one point in the story, he's explaining why he's happy that humans are exploring space, and he says, "Tonight," he thought, "even if we fail with this first, we'll send a second and a third ship and move on out to all the planets, and later, all the stars. We'll just keep going until the big words like immortal and forever take on meaning." And I love that quote so much. He goes on even further to talk about the word infinity and how we describe an infinite universe, and yet humans and life as we know it are isolated to a single point in that entire infinite space. And if we could expand, we could eventually make ourselves infinite as well, the way we describe our universe to be. So, you know, one of the things that I think really drives human desire to explore space is our curiosity for uncharted land. If we remember, our ancestors, they explored the whole world by boat. And the Polynesian Islands, the Americas, everything was founded just out of a curiosity to move onward, to see what else was out there, to see what we as humans were capable of if we expanded our horizons. And I think that's part of why we want to explore our nearest neighbors, because current technology can get us there. And I think this is why we talk about trying to explore even further when technology is able. We also have some vulnerabilities as humans here on Earth that might motivate us to move outward, but really a true understanding of all of the bodies in our solar system is so important before we go anywhere to make sure that we're making the right decision. These decisions are expensive, not just monetarily. I mean, you can imagine what one space shuttle costs. Try to move humans and items to Mars, which is about a 9-month journey away at the moment, but also just expensive in time and human power to plan these missions. So making the right decision is really important, and doing the proper research to be able to make that right decision is imperative before we try to go anywhere. And so next week I just flipped back to Neptune, but I'm going to go back to the solar system diagram that I showed earlier, because next week I'm going to be talking about asteroids and comets and meteors. And first, what is the difference between all of these objects? Why do we have an asteroid belt? Why do we have a Kuiper belt? What is an Oort cloud? You see this comet flying in our solar system down here at the bottom that's looking like it's coming from the outer solar system to the inner, and what's going on with the dynamics there. And it's really great timing because next Wednesday night we're also anticipating the big Geminids meteor shower, one of the best meteor showers of the year. And if you are interested in hearing more about that, Sunday night our Human Spirit contributor Helen Avery will be on to talk about the Gemini Twins. Their names Castor and Pollux, and she will have some great stories about all of those famed twins and famed stories. And then next Wednesday, right after my course, we will go into a live stream of the meteor shower. So I hope you stay with us and join us for that next week. We look forward to chatting with you. Keep looking up.